Hello, this is a video on the 6 trigonometric functions and the unit circle. So these are the names of the 6 trig functions. Sine, cosine, tangent are the main 3, and then cosecant, secant, cotangent are the lesser known of the 6, or the lesser used. Sine, cosine, and tangent can be found on most scientific calculators, faceplates, and the graphing calculators. Where cosecant, secant, and cotangent are typically left off of there because of their relationships with the first 3. We can basically get to the other 3 from using the first 3. Alright, let's get into the unit circle and talk about the definition, especially of these 2. And what we're also going to see is all 6, well, the other 4 can be given in terms of these first 2, the sine and cosine. Everything kind of comes back to these 2 guys right here. So let's first look at the unit circle. What is a unit circle? Well, a unit circle is a circle centered at the origin with a radius of 1. And if we look at any point on that unit circle, this point right here, let's call this the point xy. Alright, so there's the x coordinate of that point and the y coordinate of that point. And we're just talking about an arbitrary point that happens to fall on that unit circle. Well, we're used to describing that point with moving over x units, whatever the x coordinate is, and then moving up y units, whatever the y coordinate is. But we can also come up with that point kind of using what we talked about in the last video, a initial side of the positive x-axis and then a terminal side of rotating that up. Well, that length, that radius is 1 because it's a unit circle, it's radius 1, and we rotated it up theta. Okay, now every point on that circle can then be found by using a radius of 1 and an angle of theta. And this particular circle has been studied so much that we know the different coordinates of the points, or we can basically estimate any coordinates of the points by picking an x. Give me an x, and then I go up to whatever y coordinate that is, and then if you look, I've created a right triangle inside of there. So if I know an x coordinate, or I can just pick any number between 0 and 1, I can use the Pythagorean theorem because I know this is a radius 1. I can use the Pythagorean theorem to come up with y. Alright, so we could do the same thing for y if we pick a y coordinate and use the Pythagorean theorem to come up with x. So we could easily come up with as many pairs of points that we wanted, x and y. But where does this angle come in? Well, if you think about it, as I change the measure of this angle right here and I rotate this thing up, the measure of that angle will also determine a point. As I rotate up to 90 degrees, from 0 to 90 degrees, I went from this point to this point. So the angle itself can determine points on this circle. So what these first 2, the sine and the cosine, are, their purpose, their functionality, if you will, is they take in an angle measure and they spit out either the x or y coordinate. And so what we find out is the x coordinate of where we rotate, like if we're rotating by an angle up from the positive x-axis, the x coordinate is given by the cosine of that angle, and the y coordinate of that point is given by the sine of the angle. So the cosine is the x coordinate, the sine is the y coordinate. So just to kind of give you an idea, let me switch my calculator into degree mode, since we may be kind of still more used to degrees at this point instead of radians. But let's just hypothetically say this angle right here is, well, let me go all the way up to a half. Alright, to where the y coordinate is a half. If the y coordinate is a half, if I'm right here, and that y coordinate is a half, that x coordinate would then be right there. So if the y-coordinate is 1/2, we can again use the Pythagorean theorem. The Pythagorean theorem says this side squared plus this side squared equals this hypotenuse squared. So x squared plus y squared equals 1 squared, or just 1. Well, the y-coordinate is 1/2, so that's x squared plus 1/2 squared equals 1 squared, again, which is 1. So that becomes x squared plus 1/2 squared is 1/4. And then solving for x, I'll end up with x squared equals 1 minus 1/4 is 3/4. And then taking the square root of both sides, I get x is equal to, technically I get plus or minus the square root of 3 over 2. Taking the square root of 3, I get the square root of 3. The square root of 4 is 2. Plus or minus, because it's a circle, it's not a function. I could have been down here where the y-coordinate is 1/2. But I know I'm up here. I know I'm dealing with this point, so it's the positive square root of 3. So that point on here is the square root of 3 over 2 for x, and then 1/2 for y, right? And that's the sine cosine pair. Okay, now I want to show you that that angle that we're dealing with, I happen to know it. You'll learn it soon enough. We can look at your unit circle from the last section, but this is a 30-degree angle. So if I type in, and again I'm in degree mode for this, if I type in the cosine of 30 degrees, that 0.866, that's the square root of 3 over 2. Alright, and the sine of 30 degrees, that's the half. Okay, so the x and y coordinates of that point are being given by the cosine and sine of the angle of elevation off of that positive x-axis. Okay, now if I go beyond 90 degrees, if I get into this second quadrant, notice any points over here, the x-coordinate is negative and the y-coordinate is still positive. So this point right here, I'm at like halfway between here, so it's 45 degrees in the second quadrant. So that's 90 plus 45, that's a 135 degree angle from right here to here. So the cosine of 135 degrees, see, we're getting a negative number. And then the sine of 135 degrees, because we're in quadrant 2, we're going up, so the sine's still going to be positive. Alright, now notice they're the same thing, they're just opposites. That's because we're now at 45 degrees, we're on this line y equals negative x, right? If you remember from your linear functions, the line that passes through this right here in the xy plane, it goes through the origin, and the y coordinate is always the same as the x coordinate. That's the line y equals negative x. And what are we seeing? We're seeing the y coordinate, the sine, is the opposite of the x coordinate, which is the cosine. Okay, now the other 6 functions, so there's that, the sine, they're using t for the angle, but sine of t, cosine, is x and y when we're on the unit circle. Okay, now the tangent, that's the first of the other ones. The tangent is defined to be the y coordinate divided by the x coordinate. So let's go back to our unit circle and look at a point, that same point we were dealing with before. Well, this was the xy point that we're dealing with, and we're saying the tangent of the angle, this again was our angle, is equal to the y coordinate divided by the x coordinate. Well, because the unit circle is centered at the origin, I can say that this y is actually y minus 0, and this x is x minus 0, right? Y minus 0 is y, x minus 0 is x. But now what does that kind of look like? A y coordinate minus another y coordinate, right? That's the second y coordinate. X minus another x coordinate. this is like y2 minus y1 over x2 minus x1. And what's that the formula for? That's the formula for slope. So what does that mean the tangent is? The tangent is actually the slope of this line segment that connects the origin of the unit circle to any point on the unit circle. So in quadrant 1, because that line segment is a positive sloping line segment, I'm going to get a positive value for tangent, like quadrant 1 meaning from 0 degrees up to 90 degrees. So if I pick, that's called acute angles if you remember. If I pick an acute angle measure, like the tangent of 70 degrees for instance, I'm going to get a positive number because it's a positive sloping line. Alright, and if I pick something beyond 90, for instance like that 135 that we just looked at, I end up with a negative number because in quadrant 2 that is a negative sloping line. It's going downhill as I move left to right. So when I hit enter here I get -1. Now why am I getting -1 for this instead of some crazy decimal? Because remember 135 degrees, that's 45 degree angle in the second quadrant. We're on the line y equals -x. And what's the slope of the line y equals -x? It's the number in front of the x, so -1. Okay, so this quadrant 3, I am now positive sloping again, meaning I'm going uphill left to right. So if I pick something bigger than, this is 180 degrees, so I pick something bigger than that, like the tangent of, like for instance 190, I'm back to a positive slope again. Okay, and then finally I go into the fourth quadrant, something bigger. This is 270 degrees, so 90, 90, 90, that's 270, so something bigger than 270 but not quite 360, so something like the tangent of 310, just to have a number in that range. You see we're back to the negative. So the tangent is the slope of the line segment that connects the center of the unit circle to a point on the unit circle. Okay, so just a little recap. Those are the three main ones. X is the cosine of the angle. Let me get back to where that looks like the angle again. X is the cosine of that angle. Y is the sine of that angle. And the tangent of the angle is the slope of that line segment that connects the origin to the point on the circle. Okay. All right. Now think about what happens with slopes. There's a horizontal line. A horizontal line has a slope of 0, if you remember. All right, and then we've got positive slope as we're starting to increase the angle until finally we get to 90 degrees. And now we've got a vertical line. And if you remember from algebra, pre-calculus, the slope of a vertical line is undefined. All right, or you can think of it as infinite. We're getting a higher and higher and higher slope. The slope's getting steeper and steeper and steeper until eventually it's infinite. All right, infinity is not a defined number. It's just kind of an idea. So we go from a 0 slope to an infinite slope in just 0 to 90 degrees. Right, and then when we come back the other way, it's the same thing. We got another horizontal line over here at 180 degrees, or remember that's pi radians. And if we come backwards, we start increasing the negative slope, like meaning it's becoming more and more and more negative until finally it's a negative infinity. Right, it's going downhill left to right, but it's so steep it's negative infinity slope again when we get to that point. So we're going from 0 back to negative infinity back this way, and 0 to positive infinity this way. So on each side of that 90 degrees, we go from positive infinity, or approaching positive infinity, to coming up from negative infinity. All right, that's going to be very important for the next section, that you understand we're going from positive infinity on one side to negative infinity on the other, when you understand the graph of the tangent function. All right, and then remember x and y coordinates, cosine, sine, slope is tangent. Now, what about the other three trig functions? And I keep calling the other three, I call them the other three because they're the ones that's not on the faceplate of your calculator. So sine, cosine, tangent are on there. The other three are not. So that's why I always call them the other three. They're just the reciprocals of the first three. So the cosecant is the reciprocal of the y-coordinate, and the y-coordinate, remember, was the sine function. So that means the cosecant is 1 over the sine. Alright, or the reciprocal of sine. Alright, secant is 1 over x, so the secant is 1 over the cosine. Alright, and then the tangent, we saw the tangent earlier was y over x, and this is the first time I actually see the reciprocal look of this thing. There's x over y. 1 over is a reciprocal, like 1 over y is the reciprocal of y. But like if you're used to fractions like 2/3 and 3/2, that's the first time we actually see it really look like something got flipped over. But remember, this is like y over 1. So when we flip that over, we get 1 over y. So these are reciprocals in the other sense too. But because the y-coordinate is the sine and the x-coordinate is the cosine, we can write it this way as well, and get the values. Okay. All right. So we just want to practice sine and cosine, and then I'm going to, after we do sine and tangent here, I'm going to ask you immediately, all right, well, what's the cosecant of this? What's the cotangent of this based on what we get for this? Now, right now, remember, 2 pi over 3. That's a negative value. So here's the unit circle. All right, and then remember, this was pi over 6, pi over 4, the things from the unit circle that we studied in the last section. So we had those 3 values in each quadrant. And if you remember going positive, this was pi over 6, pi over 4, pi over 3. That was pi over 2. And then this is pi over 2 plus pi over 6. Right? Because pi over 6 is the first angle every time we rotate off of an x or y axis, positive or negative. So we always start off with pi over 6. So this is pi over 2 plus pi over 6. And remember, if you want to find out what that would be, just leave off the pi. So pi over 2, write that as 1/2. All right, replacing the pi with a 1, plus pi over 6, so 1/6. All right, and then change that to a fraction, and there's our 2 pi over 3. So in the positive direction, that right there is 2 pi over 3. Okay, but this is negative 2 pi over 3. So instead of going from here 1, 2, 3, 4, 5 special angles to here, we're actually going in the other direction. We're going down because it's a negative angle. Remember, that means we're going clockwise. So 1, 2, 3, 4, 5, we're going down to here. All right, and notice we end up at the same position, just the opposite y-coordinate. So what we find out with negative angles, if it's a negative angle going in there, it's the same thing as the opposite of the sine of the positive version of that angle. And that'll always be true. If you have a negative angle in there for sine, you can pull that negative sign on the outside and just find the positive version of the sine of that angle, because sine is the y-coordinate and we're rotating down instead of up. And remember, if we rotate down, the y values are initially negative. If you rotate up, the y values are initially positive, and because it's a circle, there's symmetry there for those y-coordinates. All right, now the sine of 2 pi over 3. The way I remember this, the special values going along on the unit circle, the special values you see are going to be 1/2, square root of 2 over 2, and the square root of 3 over 2. All right, and the easy pattern there is 1 is the square root of 1. All right, the square root of 1 is 1, so you can really just kind of think of it as square root of 1, square root of 2, square root of 3, all over 2. All right, and remember, just like with numbers, 1, 2, 3, they're getting bigger. The square root of 1, the square root of 2, the square root of 3 are also getting bigger. So this is the largest, This is the medium one. This is the smallest. All right. So sine is the y-coordinate. All right. The y-coordinate is the highest of these three. So it's the square root of 3 over 2 for this one. All right. Where the y-coordinate is going up this way. And of these three special angles, the intermediate ones between the axes, this has got the highest y-coordinate. So that means it's going to be the square root of 3 over 2. Okay, but remember, we rotated this way, we rotated down, so this will end up being the negative square root of 3 over 2. Alright, now, same thing for tangent. 11 pi over 6. So this time we're going to go down again, and remember this is pi over 6, pi over 4, pi over 3, and we're going to go all the way around, but remember this is 11 pi over 6. If you remember, all the way around one trip was 2 pi, and remember that rotating up was pi over 6. So 2 pi minus pi over 6, that's 12 pi over 6. Remember, 2 pi is the same thing as 12 pi over 6 minus pi over 6, which is 11 pi over 6. So in the positive direction, that number right there, rotating to that value right there, that's 11 pi over 6. But because we're going the opposite direction, we're going this way, we would actually end up right there. That's negative 11 pi over 6. All right, it's just underneath, going all the way around. It's the last special angle going back the other way. All right, now the tangent. Remember, the tangent is the slope of this line segment that's connecting the origin to that point. So, or you can think of it as just the y-coordinate divided by the x-coordinate. All right, so right here, again, the y value, if you think about how we did it before, the y value here is the lowest of those three special values. The 1, square root of 2, square root of 3. Remember, that's the values for either x or y in these three positions. So the lowest y, because it's the lowest, the smallest height at this point, so is the 1/2. So that's our y-coordinate. And then the x-coordinate, guys, because we need to do, for tangent, we need to do y over x. The x-coordinate, at this point, we are the longest of those special three. All right, we're the farthest away from the origin, left to right. So the x-coordinate is, again, how far left or right we're going. And this is the farthest away we could be without being all the way at 1. So there's, the square root of 3 over 2. There's the square root of 2 over 2 for x. And there's the 1/2 for x. Okay, so these are getting bigger. So the biggest x is right here. The smallest x is right here. The biggest y is right here. All right, the smallest y is right here. So it's the smallest y and it's the biggest x. Okay, so this is our y-coordinate. This is our x-coordinate. All right. Now it's a fraction. It's the tangent is y over x. So it's 1/2 over the square root of 3 over 2. All right, that's a fraction divided by a fraction. If you write it left to right, you can this divided by this, and I would flip that and multiply. So I end up with 2 over the square root of 3 because we're dividing by a fraction. We flip and multiply, the 2's cancel, and we end up with 1 over the square root of 3 is the value of the tangent of 11 pi over 6. Now, you can check that with your calculator. All right, make sure, because when you see pi with those those angle measures inside of the tangent and the sine and the cosine, remember those are radian measures. So make sure you're back in radian mode, and then tangent of negative 11 pi over 6, and get that decimal. It's going to be a decimal. All right, and then plug in 1 divided by the square root of 3 and verify that you get the same thing. So that way you kind of know that you did it right. Okay, so there's the same thing. Now, just to kind of give you an idea, a heads up, y over x is what we're going to get for tangent. So here we saw that it's 1 over the square root of 3. Here at 45 degrees, remember at 45 degrees, the y-coordinate and the x-coordinate are the same. We're the same, we're in the middle value for both. We're the middle of the 3 possible x values. We're the middle of the 3 possible y values. So they're both the square root of 2 over 2. So y divided by x in that case is going to be just 1. So the tangent of pi over 4, or 45 degrees, is 1. And again, you're on your line y equals x when you're at 45 degrees, so the slope is 1. Well, then if you're at the highest one, now the y value is as high as it can be, and the x value is as short as it can be. When I say short and high as it can be, I mean of these 3. So it kind of is like a role reversal. The y gets to be the square root of 3 over 2, and the x gets to be the 1/2. And in that case, we end up with the square root of 3 over 2 times 2 over 1. All right, and we end up with the reciprocal of this, just the square root of 3 over 1, or just the square root of 3. So that's not a bad thing to have on your a unit circle if you make a unit circle. As well is the values, not just the x and y, but the values of sine and cosine. So if you do a Google search for unit circle, you'll get things like this. And let me click on that. So you get things like this that have the degree measure, the radian measure, and then it has the x, y coordinate of those points. Well, remember, that's cosine and sine. So the cosine of 30 degrees is the square root of 3 over 2. The sine of 3 pi over 4 is the square root of 2 over 2. All right, but that's what I was talking about before, is it's always going to be square root of 3 over 2, square root of 2 over 2, or 1 over 2 for all these values. And notice this is 3, 2, 1, 1, 2, 3, 1, 2, 3, 3, 2, 1. It's just, it has that pattern over and over again. But because it's that pattern over and over again, the y is just, or sorry, the tangent is just y over x. You always get that same pattern for tangent. So it's not a bad idea when you search for one of these and print one of these out. I'd go ahead and print one out to have access to it. But just use the fact that the tangent here, that's not a very steep line. The tangent here was 1 over the square root of 3, we just saw. All right, the slope here was 1. Okay, and then the slope here, this steep line right here, is the square root of 3. Okay, so because these things flip from 30 degrees to 60 degrees, the y-coordinate becomes the x-coordinate, the x-coordinate becomes the y-coordinate. We just get a reciprocal because the tangent is y over x. And then here in the middle, it's always 1. And then over here in the quadrant 2, you're going to get -1 for tangent. Here, this is the steep slope, right? It's kind of the mirror image of that. So we get a negative square root of 3. That's steeper than 1 over the square root of 3. So that means this one is -1 over the square root of 3. All right. So there's a pattern with the sines and cosines. That makes for a pattern with the tangents. All these on the outside here are the tangents of the angles. These first values are the cosines of the angles, comma, and these second values are the sines of the angles. So all the points that are given you on the unit circles are sines and cosines. And then if we divide the y-coordinate by the x-coordinate, we're always going to get these all the way around, right? Positive or negative, okay, based on the sines and cosines, because it's division. Negative divided by negative is positive, so we'll get positive tangents. All right, positive divided by negative is a negative, we'll get negative tangents. But notice this line right here is also the same as this line right here. It just comes straight through. So the tangent is the slope of that line. It's the same line on both sides, so the tangent here is also going to be -1 over the square root of 3. Okay, and you can just use that property to find out all of these different values for sine, cosine, and tangent. So a really great idea, just to Google search unit circle and then print one of these out. Have it with you when you're doing your homework, because you're going to need to know what is the sine of pi over 2. There it is. What is the cosine of 5 pi over 6? Cosine's the x-coordinate, so there it is. What's the tangent of 11 pi over 6? There it is. All right. So the unit circle, there's a lot of patterns to it. There's a lot of symmetry there, and it's basically getting this first quadrant down. And then once you have the first quadrant down, just thinking about the signs, not sine, but the signs of the numbers that would be in each quadrant, and that'll get all your values along with their signs correct. All right, so there's the sine and the tangent of these two numbers. Now I ask you, what if I ask you for what's the cosecant of negative 2 pi over 3? Well, the cosecant of negative 2 pi over 3 is the reciprocal of the sine of negative 2 pi over 3. The sine of negative 2 pi over 3 is the square root of 3 over 2, negative. So the cosecant is going to be negative 2 over the square root of 3. All right, we just flip it over. All right, the tangent of negative 11 pi over 6 was 1 over the square root of 3. So the cotangent of negative 11 pi over 6 would be the square root of 3 over 1. Okay, so we just take the reciprocal of these because that's what this is telling us to do. To find the other three trig functions, we just take the reciprocals of those first three, the sine, the cosine, and the tangent. Now a couple properties. This will be really important for the next couple sections. The domain and range of sine and cosine. So because it's defined on a unit circle, the domain, remember sine and cosine are the x's and y's. Let me go back up to the original one we did. Right here, well, this will be fine. We can keep this angle going around and around and around as many times as we want to. So the domain is all real numbers, negative infinity to positive infinity, because we can just keep going around and around. But the sine is the y-coordinate. What's the biggest y-coordinate on the unit circle? It's positive 1. What's the smallest on the y-coordinate on the unit circle? It's negative 1. All the other y-coordinates are somewhere in between. So the domain is all real numbers, but the range is from negative 1 to positive 1. And that's the same way for cosine, because the biggest x and smallest x is also negative and positive 1. So the domain for both of these trig functions is all real numbers, and the range is between negative 1 and positive 1. Alright. Even and odd properties. The cosine. So what this is saying is if I go up to some point on here, if I get up to some angle measure, so that's some positive angle measure, and I get an XY pair, I'm at some point on this circle at that angle. What this is saying is if I went down by the exact same angle to where the angle was the same, it's just the opposite sign, meaning I went, instead of counterclockwise, I went clockwise, so that would be a negative angle. What it's saying is where I end up would have the exact same x-coordinate. Remember, cosine is x-coordinates. I'd have the exact same x-coordinate, but the sine is going to be opposite. Right? The y-coordinates are opposite of each other. So it's the same distance above and below, but because we're going above, this sign is positive, and we're going below, this sign would be negative. Okay, but the actual values would be the same. Whatever this x is the exact same. But whatever this y is, this y would be the exact opposite. Right? Same number but opposite sign. So instead of a positive 0.44 here, if we were down here, it'd be a negative 0.44. Right? So that's what this property of even and odd function says. Now for sine or for tangent, remember that's slope. So whatever the slope is here, it's a positive slope. If we rotated the same amount, we would have a negative slope of the exact opposite sign of what this positive slope is. Okay, the slope. Remember, slope is just the change in y divided by the change in x. So it's a negative y over x. This is a positive y over x. So it's the same thing. It's just opposite. All right. So cosine ends up being the exact same. Sine and tangent, though, are opposites of what they were before. Okay, and because cosine, cosecant, cotangent are these reciprocals. They end up having the same properties that the original of these three do. Alright, that's the even and odd properties of these guys. Alright, quotient identities. Tangent is sine over cosine. Remember we said tangent before was y over x. Well, y is the sine, x is the cosine, so we can say tangent is sine over cosine, and that is true. So that would mean cotangent, since that's the reciprocal of tangent, well, that would be cosine over sine. And earlier on another slide we said that was x over y. So again, that's the same thing. Alright, and then the domain and range, we already talked about that. Domain and range is sine and cosine because of the rotation. Alright, the Pythagorean identity. So this is a very important identity. Sine squared plus cosine squared equals 1. So where does that come from? Well, pick a point on the circle. It doesn't matter where we pick it to be. That's x and y, right? And because this is the unit circle, from the origin to that point, that's a radius of 1. Right? And if we come down here, we make a right angle. And what's this length right here? Well, that's how far over we go to get to the x coordinate of that point. So that means this is x. The height here is y. So we got a right triangle, and that's x squared plus y squared equals 1. But in the unit circle, x is the sine function, y is the cosine function. So we end up, or sorry, backwards. X is the cosine function, y is the sine function. So we end up with cosine squared t plus sine squared t equals 1. Now notice that we put the squares for these trig functions. Instead at the end, instead of writing cosine of t squared, we put it right there. And the reason why we do that is to not have to put the parentheses and then not have to confuse like cosine t squared with cosine of t first and then square that. Right? This looks like I need to square t and then put it in the cosine. This looks like I need to put t in the cosine and then square it. Okay, so to avoid that confusion, if I didn't have this outer set of parentheses in this expression, it would be very confusing as to what I meant. Am I squaring t or am I squaring cosine of t? And you do get two completely different things, just so you can see it. If I take the tangent of 5, well, let's do cosine. If I take the cosine of 5 squared, or if I take the cosine of 5 and then square it, I get two completely different things, right? Drastically different. So make sure that you understand the difference between that. And so when we mean plugging into the sine and cosine first and then square, we'll put that power in between the sine and the input. Okay, but it's just the Pythagorean theorem. That's why they're called the Pythagorean identities. It's the x and y coordinates that make up that right triangle. We can be replaced with sine and cosine. Right, now from that, if I take sine squared t plus cosine squared t and I divide this whole entire thing through by the sine function, sine squared t, if I divide all of them, I'm just dividing the left and right side by the same thing, I end up with 1 plus cosine divided by sine. If you go back and look at our reciprocal identities from before, cosine divided by sine is cotangent. So that's cotangent squared t. And then 1 over the sine, if you go back and look, that was cosecant squared t. Alright, so 1 plus cotangent squared equals cosecant squared. Sometimes this is written as cotangent squared t equals cosecant squared minus 1. We'll subtract the 1, put it on the other side. And then if I start off with that sine squared t plus cosine squared t equals 1, and I divide now by cosine squared t on both sides, I end up with tangent squared. Sine divided by cosine is tangent squared t plus 1 equals 1 over the cosine squared was secant squared t. So these three make up what's known as the Pythagorean identities. They all come from the Pythagorean theorem, and they all come from, the other two can be derived, from, let me move that back down. The other two can be derived from that first one, the main one, the sine squared plus cosine squared equals 1. So that's why these are called the Pythagorean identities. They come from the Pythagorean theorem. All right, now how might I use those? Well, notice right here I've got sine t equals 3/5, so that's 3/5 right there, and that's being squared equals, plus cosine squared. That's the sine squared, right? Plus cosine squared equals 1. All right, I can square both of these. Square 3, I get 9. Square 5, I get 25. Plus cosine squared t equals 1, and now I can solve for cosine. I can subtract 9/25 from both sides. All right, 1 minus 9/5, that's 25/25 minus 9/25, that's 16/25, and you can just do that on your calculator too, equals cosine. Now I'm going to take the square root of both sides to get cosine by itself. The square root of 16/25. Now technically I need a plus and a minus, because when you solve via square you got to consider it could have been negative. This ends up as 4/5. Alright, plus or minus for right now, but notice they give me, this is between 0 and pi over 2. So remember, this is 0, this is pi, so this is pi over 2. Remember, 180 degrees was pi radians, so pi over 2 is 90 degrees. So between 0 and pi over 2 means we're up here in quadrant 1. Alright, and in quadrant 1, cosine, that's the x coordinate, remember that's x. In quadrant 1, cosine is positive, so we don't have to consider the negatives. The cosine will be 4/5. Alright, so anyway, that's how we use that Pythagorean identity. That's why it's important. If we know sine and we know where we are, which quadrant we're in, we can find cosine. Okay, now if we had been in quadrant 2, for instance, sine is positive in quadrant 2 also, because it's above, the sine is the y-coordinate, we're above the y-axis there, then cosine would have been negative, and our answer would have been the negative 4/5. So it's all about where we are. That's very important when they give you this, because that'll determine the sign here at the end. Alright, the periodic properties. If you give me an angle and I add 2 pi to that angle, it's like we were talking about before, I'm going to be right back to where I started. Like the y coordinate, when I rotate back around, wherever I am on that unit circle, if I'm at some particular angle, the sine and the cosine are the values of where I am at that point. That's cosine, that's sine for some angle. So what this is saying is, if you just go around another 2 pi, and it really can be any multiple of 2 pi, then you're right back to where you started. The angle is now t plus 2 pi, and since 2 pi radians is 360 degrees, you're right back where you started, so the x and y coordinates are the exact same thing that they were before. So we're right back to the same thing. Alright, so that's what a period means, and that'll be really important in the next section. But the period, that's how long it takes to get not only back to the exact same y coordinate, but also the exact same x coordinate. Like, for instance, what I mean by that is we're back to the same y coordinate, like right here, before we go all the way back around, but the x coordinate's not the same. So when we're right back to the exact same y and the exact same x, that's a period of 2 pi. That's what it takes to get all the way back around to where we started. So these are called periodic functions, and it's because they we end up eventually getting back to where we start when we add a certain angle. That certain angle that guarantees that we're back to where we start is the period. Alright, what about the tangent function's period? Alright, let's pick two different points here. Let's pick one right here, and then we'll pick another one right here. Alright, now you'll see why I'm picking 2 points in a second. So let's say our initial side is over here. Let me do a dashed line. So this is the initial side for that blue line. Now, how long is it going to take until I get back to that exact same slope? Remember, the tangent is the slope. So right now, this is our initial angle t. All right, and we're going to start rotating until we have that exact same slope again. Well, if you're thinking on your toes, you'll realize that all I got to do is extend this through the origin, come out the exact same distance on the opposite side, and because that makes a straight line, that'll obviously be the exact same slope. This slope and then this slope. So what did I do to get from here to here? What did I rotate? Well, that's a straight angle. That's 180 degrees, which is the same thing as pi radians. Okay, now this is where the other one's coming into play. Is that always going to be true? So let's start from the other one. I'm going to color this one red. So there's my initial side for this one. How much do I need to rotate until I get the same exact slope? Well, like I said before, I can just go right back through the origin, because that line is still this exact same line, so they have the same slope. And then how much did I add to this angle? This is like T1. Now this is like T2. How much did I add to this angle to get back to this this other line segment that has the same slope? So I went from there all the way around to there again, which is again a straight angle. Because we're always having to go right back through the origin to make a straight line, we're always going to be adding pi radians to get to that. So the period for tangent is pi. Okay, a little bit different from sine and cosine. Sine and cosine have a period of 2 pi before we get back, because we have to get back to the exact same spot, not just the same spot for x or the same spot for y. We have to get all the way back around to where we're both the same. So that's why the period's 2 pi. But for tangent, the period is only pi, because it just takes going back through the origin and creating a straight line to have the exact same slope again.